Hey guys, welcome to the third video in the alkene carbocation unit. And so this video is going to be covering two of the carbocation rearrangements, okay? And so the first is called a hydride shift. So I gave you guys here an example of an alkene. So using the first reaction I showed you, I'm going to keep that part consistent just because you don't know any others. We're going to go through this reaction and show you guys how it can rearrange, okay? And so let's use what we've seen from the previous videos of how this is going to react. The double bond is going to come in. It's going to attack that hydrogen. This bond is going to break. And so our product, or the intermediate of this reaction, right, we're going to have a chlorine here, negative charge. And so let's remember how carbocations form. Carbocations like to form the more stable carbocation. So we can form it on this secondary or this primary. Remember, secondary carbocations are more stable, so we will be forming the secondary carbocation, and the hydrogen adds there. Okay? Remember, given the choice, you form the more stable carbocation always. There's no exception to that rule. Okay? And so, what happens now? Now, you may be tempted immediately to attack that carbon, but we need to take a step back. Okay? What you need to do is examine the carbons on both sides of the carbocation, only the ones immediately next to it. You don't go more than one away. So we're going to be focusing on that carbon and that carbon. And what we need to do is we need to see if it's going to be if I were to move a carbocation, will it be more stable on any of the adjacent carbons? Okay? So what I want to do, I'm not going to draw any arrows, I'm not going to do anything fancy. Draw out the two possibilities of if I move it. Okay? So if I moved it to the left, it would move over there. And if I moved it to the right, it would move there. Okay? And so here, I'll just draw our hydrogen there, just so we all know that it's still there. All right? And so out of the three that we now have, right, number 1, 2, and 3, which is the more stable one? On number 1, we have a secondary carbocation. Okay? Number 3 is going to be a primary carbocation. So primary carbocations is one of the more unstable ones. On number 2, we have a tertiary carbocation. If we remember from our carbocation stability, the tertiary is going to be more stable because it has more electron donating groups that help stabilize that positive charge. So our tertiary carbocation is more stable than all three of these. And so here are where shifts come in. So I'm going to erase all this stuff right now. Okay, and here are where shifts come in. When we want to rearrange a carbocation, we can only move it a distance of one carbon, and only one carbon, okay? And so, let me just erase that. Yeah, and so only one carbon distance. And how exactly does it move? Well, again, there are a couple ways that they can do it. In this case, we're going to be covering a hydride shift. So what I'm going to do is I'm going to draw a hydrogen off of the carbon that we're going to move it to, okay? And the way that we draw the curved arrows is we need to start it from the bond. Remember, the bond has 2 electrons. And so in this case, the hydrogen is taking its electrons with it. This is very different from when you've seen it when we reacted with, like, let's say HCl and a base like OH minus. The curved arrow for that is the H is going to be attacked, but the bond goes to the chlorine. So the H isn't taking any electrons with it. In this case, it is taking electrons with it. That's a key thing to remember. That's why it's called a hydride. And so the arrow is going to be starting from the bond and end at the carbon over here. So the chlorine isn't going to come into play yet. And so what we have is the hydrogen has now moved here. Our blue hydrogen that we added is still there, but now the carbon to the left of where our carbocation used to be doesn't have a full octet anymore. So it's going to have a positive charge, okay? And so what we did is we went from a lower stability carbocation to a higher stability carbocation. And the key thing about rearrangements, and this goes for all types of carbocation rearrangements, is that they will only occur if the carbocation that we form, the new carbocation that we form, is more stable than the previous one. Not the same stability. If I'm going from a secondary carbocation, right, secondary carbocation, to a secondary carbocation, won't happen. If I'm going from a secondary carbocation to a primary carbocation, won't happen. But secondary to tertiary can definitely happen and will happen, okay? And so that's the thing. And the other thing about carbocation rearrangements is that they always occur, all right? If you have a carbocation and it can shift to give it better carbocation, it's going to happen, okay? And if you're having a little bit trouble visualizing what we did here, let's try to draw it a different way. Instead of the one curved arrow I drew, there's our carbocation. Let's take it in a couple steps just to really drive it home. So here is my hydrogen. I'm going to draw an arrow taking the electrons in this bond, and I'm going to now just put it on the hydrogen itself. So what this is going to give us, we're still going to have this carbocation, but now we're going to have a positive charge on that carbon because it just lost a bond. It just lost 2 electrons. We have a hydrogen now with 2 electrons and a negative charge, right? And we still have our hydrogen over here. And so now that hydrogen has to pick where it's going to attack. Is it going to attack the tertiary carbocation or the secondary one? Well, we have to look at the substituents off of each carbon. This one, the tertiary carbocation, has 3 carbon groups coming off of it. That means that it has 3 electron donating groups that help stabilize that carbon and make it less positive. Because it's less positive than our secondary carbocation, that negative charge on the hydrogen and its electrons, who are negatively charged, will not be as strongly attracted to it, okay? And this is going to introduce some vocabulary terms that you guys are going to be hearing throughout Orgo 1 and 2, called a nucleophile and an electrophile, okay? So nucleophile and an electrophile. Now, nucleophiles are what attack, okay? So in this case, we know our chlorine with the minus charge in the end will attack our carbocation. So it is a nucleophile. The electrophile is what's being attacked. Electrophiles are usually deficient in electrons. Nucleophiles usually are rich in electrons. Okay, so from now on, I'm going to be trying to use these vocabulary words, so you guys should get used to them, and you'll be hearing them a lot more in lecture from now on. Okay, and so which carbon is the more electrophilic carbon? It's the carbon that's going to be the easier target for negative charged electrons, therefore the more positive carbon, or the carbon with less substitution on it. And so our hydrogen, our hydride, because it has a negative charge, it's going to come in, it's going to attack that carbocation, and it's going to result in this structure here, hydrogen, the hydrogen that we shifted, and now our carbocation this way. All right, and so that is a hydride shift, and then our chlorine again is just gonna come in over here. Oh, that was a bad arrow. So it's going to give us this structure here, and here is our hydrogen that we originally added, and here is the hydrogen that we shifted. So that's a hydride shift. Our next shift is an alkyl shift. So let's start with the same reaction, right? Our arrow double bond attacks the hydrogen, then that chlorine bond breaks. So we have, again, the choice between the primary and secondary carbocation. The more stable one will form, therefore the secondary carbocation. Here's our chloride anion. And so, oh, this is a bad mistake. No, not bad mistake, just bad example. Here, I'm going to change up the molecule. Okay, let's make this a little neater. So I'm changing up how our molecule looks, and you'll see why. And so an alkyl shift is the same concept as a hydride shift, all right? But instead of moving a hydrogen, we're now going to be moving an alkyl group. It could be a methyl, it could be an ethyl. It doesn't really matter, all right? And so how do we show this, right? Well, again, and remember the principal concepts that we're only going to rearrange if we can form a more stable carbocation, okay? And so what we do is I'm going to pick one of the methyl groups. It doesn't matter. And I'm going to just draw over it CH3. And the arrow is going to be the exact same thing. The electrons from the bond are going to come in and attack that carbocation. And so we're going to still be left, remember, keep everything that you know is the same. And we're going to have our chlorine over here. And so what happened is we moved that CH3 onto here. And now we're going to have a positive charge over here. And the chlorine can now come in and attack. So our product, the chlorine, we're going to have our CH3 group right over here. And also I didn't include the hydrogen that was added, but let's just draw that in real quick. Our hydrogen over there. Okay, and that would be our answer. So again, we went from a secondary to tertiary carbocation. So we followed that rule that a carbocation shift only occurs if we will increase the stability of the carbocation that we form, right? And so the reason we did an alkyl shift in this case is because we didn't have a hydrogen to use. We didn't have a hydrogen on this carbon right over here. If you took a look, there's no hydrogen over there. So we had to use an alkyl group. And remember, it's not confined to methyl groups. Don't make that mistake, okay? That's just the most common example, okay? And if you're having trouble visualizing how we did this, again, let's take it in one step at a time, how we did it up there. We're gonna, we're gonna do this step first. Right, so our hydrogen attaches there, and here's our positive charge, and here's our CH3. And so we're going to break the bond of the CH3 and put it onto the carbon. So we're going to get this structure here, positive charge, the positive formal charge there, positive formal charge there, and a CH3 minus. Okay, a CH3 minus. And so now it has the choice of where it's going to attack. And so our question is, what is the strongest electrophile? Or what's the most electrophilic carbon? The more electrophilic carbon will be the one that is more electron deficient, right? Remember, looking at the word electrophile, we have electro for electron, and then philic, it has an affinity for them, and positive charges attract negative charges. Therefore, the more positive your charges, the more the electrons will be attracted to it. The less positive your charges, the less the electrons will be attracted to it. And so, because we have 3 carbon groups here that donate electron density over there, that positive charge is going to be a little bit smaller. right? So here we have positive charge is going to be a little bit smaller, whereas the carbon on the right, if we look at it, is going to have that carbon group and that carbon group donate density. So it's not going, so it also is somewhat stabilized, just not enough. So it's going to be a little bit smaller. But again, it's going to be more positive, and so therefore our CH3 minus comes in and attacks at that carbon. And so now we're going to have that carbocation. And then the reaction proceeds as above. But remember, we don't draw these as separate steps. We only draw it with the one arrow, as we do right there. And the arrow starts from the bond and it goes directly to the carbon. Okay? And so remember, carbocations can only shift the distance of one carbon, and only one. Never two, never three, never four, so on. Okay? And so next video, we're going to be covering another rearrangement. I'm making it its own video because a lot of people get tripped up over it, and it is somewhat confusing in the beginning, and it's like a subset of an alkyl shift, okay? But it is an extremely common question to be asked on the test, and there's no reason to get it wrong, and if you follow a couple strategies, a couple of simple steps for them, you'll get them right every single time, okay? And so I will see you guys in the next video. If something here didn't make sense, please feel free to email me. Go to the CLC. The TAs there are great. They're there to help you guys. And I'll see you in the next video. Good luck.